The ground beneath your feet feels solid, permanent, but that's an illusion. The Earth's surface is a jigsaw puzzle of colossal rock slabs called tectonic plates. They float on a sea of semi-molten rock, constantly in motion, grinding against each other at about the speed your fingernails grow. Most of the time, this movement is silent, imperceptible. But where the edges of these plates meet, at fault lines, they don't always slide smoothly. Their rough surfaces catch and they get stuck. While the edges are locked by friction, the rest of the plates keep pushing. For years, decades, sometimes centuries, the rock along this locked fault line bends, deforming like a ruler pushed against a desk. It stores an incredible amount of elastic energy. This is the essence of the elastic rebound theory. The rock stretches and stretches until the built-up stress finally overpowers the friction holding it in place. In an instant, it snaps. The fault ruptures and the rock on either side springs back, suddenly offset from where it was moments before. That sudden, violent release of stored energy is the earthquake. The point deep underground where the break begins is called the hypocenter. The spot on the surface directly above it, the epicenter, is where the shaking often feels strongest. That released energy doesn't stay in one place. It radiates outwards in the form of seismic waves. First come the P waves, or primary waves. They're the fastest, a compression that pushes and pulls through the rock like a sound wave. You might feel this as a sudden jolt or hear it as a bang. Seconds later, the S waves, or secondary waves, arrive. They shake the ground violently from side to side. But the real damage often comes from the surface waves, which travel along the ground like ripples on a pond, causing the rolling and shearing motions that can bring down buildings. When you hear about an earthquake's size, you're usually hearing about its magnitude. This measures the total energy released at the source, a single number for the whole event, calculated on what's called the moment magnitude scale. But intensity is different. It's what you actually feel at your location. The intensity can be severe near the epicenter, but mild just 100 miles away. It's the difference between the raw power of the event and how strong the shaking is where you're standing. While the vast majority of earthquakes are tectonic, born from this slow dance of giant plates, we've learned that we can sometimes wake the ground ourselves. The main culprit isn't the process of fracking, but the disposal of massive amounts of wastewater from oil and gas operations. When this water is injected deep underground into disposal wells, it can increase fluid pressure on ancient dormant faults. It acts like a lubricant, reducing the friction that holds the rock in place, sometimes triggering swarms of earthquakes in places that rarely felt them before. The sheer weight of water in massive reservoirs behind dams can do the same, pressing down and lubricating faults below. We live on a restless planet. Scientists can map the faults, they can measure the strain building up with GPS, and they can forecast the probability of a quake over decades. But predicting the exact moment a fault will finally break remains beyond our reach. The forces are too vast, the system too complex, buried miles beneath us. So we listen. We measure the rumbles and the slow, silent stretching of the rock, not to predict the inevitable, but to understand it. And by understanding, we learn to build better, to prepare smarter, and to respect the immense hidden power that shapes our world.